For decades, hypercars were powered by roaring engines and gasoline-fueled speed. But in 2025, the game has changed, and the fastest machines on Earth are now electric. In this video, we're exploring the future of hypercars and how EVs are breaking speed records in 2025. From cutting-edge designs to mind-blowing acceleration that leaves even supercars in the dust. And trust me, the record-breaking model at the top of this list will redefine what you think a car can do. Before we hit the gas, don't forget to like, subscribe, and tap the bell, because the future of speed is silent, but unstoppable. Instant torque is demolishing acceleration records. Electric hypercars have one unbeatable edge: instant torque. Unlike gas engines that need RPMs and gears, EVs deliver maximum power the moment you hit the pedal. The Rimac Nevera proved it with a 0 to 60 in 1.74 seconds, the fastest ever. The Lotus Evija and Aspark Owl are close, both aiming for sub-2-second runs. This isn't just hype. The physics favor EVs, as they hit peak torque from 0 RPM, while combustion engines peak much later. Multi-motor systems push this further, like the 1,900 Pininfarina Battista, which uses 4 motors and all-wheel torque vectoring for unmatched grip and acceleration. Battery technology is unlocking sustained performance. Early electric hypercars have insane speed but poor endurance. That's changed with advanced battery cooling. The 2025 generation uses liquid-cooled packs and active thermal systems to keep power consistent, even on track. The Rimac Nevera's 120 kilowatt-hours pack, for example, runs at full output without overheating thanks to integrated coolant channels. Now solid-state batteries are entering production, offering higher energy density, faster charging, and superior thermal stability. Companies like Factorial Energy and QuantumScape are partnering with hypercar makers for launches in 2025 to 26. Add silicon anodes, boosting capacity by up to 30% and cutting charge times. And the next wave of EV hypercars won't just be quicker, they'll sustain that performance longer. Aerodynamics and active systems are maximizing top speed. Electric hypercars are showing that top speed takes more than horsepower. The Lucid Air Sapphire tops 200 miles per hour, while new prototypes aim for 250 plus. The secret is advanced aerodynamics. Cars like the Mercedes-AMG 1 use active aero, front flaps, wings, and diffusers adjusting in real time based on speed, steering, and braking. Hypercars now process sensor data hundreds of times per second to fine-tune airflow faster than humans can react. Ground effect tech, once racing only, is back too. By controlling airflow underneath the car, engineers create huge downforce without massive drag. The Gordon Murray T50 pioneered fan-assisted ground effect, and EV hypercars are pushing it further with independent electric fans for consistent grip at any speed. Weight reduction through material science. The biggest challenge for electric hypercars has always been weight. Batteries are heavy, and performance cars need to be light. Material science is finally catching up. Carbon fiber construction is now standard, but 2025 has brought new manufacturing techniques that make it lighter and stronger. Automated fiber placement allows engineers to optimize material layering for specific stress points, reducing weight while maintaining structural integrity. Some manufacturers are achieving curb weights below 1,800 kilograms despite carrying massive battery packs. The Lotus Evija targets 1,680 kilograms through extensive use of carbon fiber in the monocoque, body panels, and even suspension components. Aluminum and titanium are being used strategically where carbon fiber isn't suitable, with 3D printing allowing for hollow structural components that would be impossible to manufacture through traditional methods. Battery packaging efficiency has improved dramatically. By integrating batteries into the structural platform, rather than simply mounting them as separate modules, engineers are eliminating redundant structures and lowering the center of gravity simultaneously. This structural battery approach means the pack itself contributes to chassis rigidity, allowing other components to be lighter. The result is better weight distribution, lower polar moment of inertia, and improved handling dynamics that help these cars translate their power into actual speed on real roads and tracks. Charging infrastructure is eliminating range anxiety. Practicality has long been a knock on electric hypercars, but ultra-fast charging is closing the gap. Today's 800-900V systems deliver speeds that seemed impossible just years ago. The Porsche Taycan Turbo-S adds 200 kilometers in under 10 minutes on a 350 kilowatts charger, while hypercars are pushing past 500 kilowatts. Rimac Tech can hit 80% in under 15 minutes without overheating, thanks to advanced thermal management. Private high-performance networks are rolling out with liquid-cooled cables to handle massive power safely, and hypercar makers are partnering globally for access. Solid-state batteries promise even more, potential full charges in under 10 minutes. Soon, charging a hypercar could be faster than filling a gas tank before a track day. EVs are dominating in motorsport development. Racing has always fueled road car innovation, and electric series are speeding hypercar progress. Formula E advanced powertrain efficiency, battery management, and region braking, all now in production hypercars. Extreme E proved EVs can survive brutal conditions, from deserts to Arctic ice. Manufacturers use racing to stress test tech like torque vectoring, thermal management, and predictive power delivery before refining them for million-dollar cars. The pipeline is faster than ever, with software-driven systems. A race-winning battery algorithm on Sunday can be tested in prototypes by Tuesday and pushed to customers via over-the-air update weeks later. The sound and experience are being reinvented. A common critique of electric hypercars is the loss of engine sound and connection. Manufacturers are countering this with synthetic soundscapes and feedback systems. The Dodge Charger Daytona EV uses a 126 decibel Fratsonic exhaust that responds to performance, while Lotus amplifies natural motor and inverter sounds to create a futuristic soundtrack. Beyond audio, haptic systems in wheels and pedals give drivers physical cues about grip, power, and braking, replacing vibrations once provided by engines and transmissions. Instead of faking tradition, EVs are building a new kind of driver-machine connection. Production numbers are increasing and prices are coming down. Electric hypercars are shifting from ultra-rare to slightly broader production. Rimac and Pininfarina each built 150 units, small, but far more than the single-digit runs of early EV exotics. More importantly, their tech is filtering down. The Lotus Elevator borrows from the Aviga, while Lucid, Mercedes, and Porsche are using hypercar innovations like torque vectoring, thermal management, and active aero in high-performance sedans. Within 3 to 5 years, $150,000, $250,000 electric sports cars could rival today's million-dollar hypercars. Unlike complex V12s, electric motors are simpler, and battery costs are dropping 15 to 20% annually, accelerating the trickle-down of hypercar performance. From instant torque to futuristic designs, 2025 proves that EV hypercars aren't just competing with gasoline, they're leaving it behind. Which record-breaking car blew your mind the most? And would you ever trade the roar of an engine for the silence of electric speed? Drop your take in the comments, I'd love to know. If you enjoyed this look into the future of hypercars, hit like, subscribe, and share this video with a fellow car enthusiast. Until next time, stay curious, stay inspired, and remember, the future doesn't just run fast, it runs electric.